start kind of the basic idea on this. So concavity is talking about a certain type of shape that a graph looks like. So basically, just to kind of start you with the idea, concavity, like where you hear the word concave is usually with a mirror or a lens. Like a concave mirror typically kind of looks like this. It caves in, okay? When I was a kid, I used to take my mom's mirror because it was, when you do your makeup, and it was concave. And if you go outside and let the sun, you can make a fire start that way. So that's what I used to do with her mirror. Okay, if it's convex, it doesn't work like that. But concavity, man, you can make some fires and stuff with that. So it's a lot of fun. So concave up it basically means the shape's going to kind of look like that, kind of like a parabola that's opening upwards. It can also be half of that. So all of those shapes, those three shapes right there are all concave up. And then concave down would just be the reflection of that. So if you're concave down, it would be kind of like a parabola going downward, or it would be like part of that. It's either the full shape or half of it like that. So that's kind of just in general what concavity means. In calculus is you have graphs that have that kind of shape to them. And calculus can be used to find that. And one of the things we'll look at as far as a business application is what we call diminishing returns, which you typically might talk about in some economics class or something. So a little bit more specifically, concave up, you're going to always name your concavity on an open interval, just like you did increase decrease. What it really means is if you're concave up, the slope of the tangent line is increasing, okay? And I'll kind of show you on this diagram down here in a minute. So it means the slope of the tangent line's increasing. So if you look at this part right here, you're concave up in this part right here. I'm just going to kind of highlight that. That would be kind of going up. And if you look at those tangent lines, doesn't it look like the slopes are getting bigger? Okay, they're getting steeper, right? Okay, this tangent line right here is less steep than this. So what these tangent lines are doing is one thing that you probably want to write a note on here is basically the tangent line's slope gets bigger. So if you're concave up, that's what happens to the slope of a tangent line. It just gets bigger and bigger. It gets steeper and steeper. The graph gets steeper. That's what concave up means. So if you look at that shape, that's what you would end up having. Okay, if you're concave down, that would tell you that the slope of the tangent line is decreasing. Okay, so if I kind of highlight this, like in this blue color here, okay, well, what's happening on that is the tangent lines are getting smaller. Okay, so if you look at this, you kind of have a big tangent line, a real steep tangent line right there. And then when you're over here, that tangent line doesn't have as much steepness. So if you're concave down, the tangent lines get smaller. When you're concave up, the tangent lines get bigger. Does that make sense just visually to you? Okay, all right. So tangent lines, it's really measuring how a tangent line is changing. Okay, so what this means is concave up just means the first derivative is getting bigger. Okay, and concave down means the first derivative is getting smaller. Okay, remember the first derivative measures the slope of a tangent line. So at concave up, the derivative gets bigger. Concave down, first derivative gets smaller. That's what happens in that case. Okay, another terminology, we have an inflection point. An inflection point would just be a defined point on the graph where the concavity changed. So on this point right here on this graph, we would call that an inflection point. And the reason it's an inflection point is because the concavity changed from down to up, or vice versa. If it changes from up to down, that's an inflection point. Okay, so you could also have a situation kind of like this. Okay, right here, you're concave up. Right here, you're concave down. So that point where the concavity changes is going to be what we call an inflection point or a point of inflection. Okay, so that's kind of the terminology of concavity. It's talking more about a shape of a graph, and it's a measurement of how the first derivative changes. Okay, that's the idea. Okay, so on this next page, the next thing we want to kind of talk about here, and we did this earlier in the semester, I don't remember where, but I think we were working with a little physics example, and we have what's called a second derivative. So a second derivative just means you do the derivative of the first derivative. You do it again. We usually notate that by f double prime of x, or the Leibniz notation would be d2y over dx2. Now, those are not exponents. That's just the way Leibniz created the derivative. If you went higher, we'll never go to a higher derivative in this class, but you could theoretically do as many derivatives as you want to. Third, fourth, fifth, and so forth. Okay? So like what in physics, it goes like this, and you don't really have to know this. The first derivative is velocity. Second is acceleration. The third is called a jerk, which I always thought was kind of interesting. In physics, the third derivative is a jerk. Okay, so you want to take physics and learn about that, you can. But you don't have to know that. Okay, so down here, there's a couple of things. If you're going to determine concavity inflection points, what you have to do is you have to work with the second derivative. Okay, now this is kind of tricky for a student to grasp immediately. You have to think about this a little bit. What you're doing is whenever you are concave up, the first derivative is getting bigger. Okay, now we learned how to analyze whether a function's increasing or not, right? Remember what we did? We did a derivative, then we did a sign chart. So if you're looking at where a derivative is increasing, then you have to do the derivative of the derivative, which is kind of weird, but you're doing the same thing. So if you analyze where any function's increasing, you take a derivative of it and you make a sign chart to see if it's plus or minus. So since you're looking at how the first derivative increases, that's why you do the second derivative. Okay, you got to think about that a little bit, but that's going to be the technique that we're going to use. Okay, so what we're going to look at, down here, this just basically kind of gives an illustration of some of the things that you would see. Okay, right here, if you look at this piece right here, I'll try to highlight this. You're concave down right there. And then this shape right here that I'm highlighting in blue, you would be concave up. Okay, now this thing right here, when the second derivative is equal to 0 and the concavity changes, that gives what you call an inflection point. So what we're going to end up doing is we're going to do sign charts to analyze concavity, and you try to figure out where the second derivative is 0, just like you did the first derivative, and then you do a sign chart to figure out how the concavity goes. Okay, another illustration would be this entire thing right here is concave up. That's the entire, kind of think of a smiley face on that. And in this case, this is not a point of inflection. And the reason it's not a point of inflection is the concavity didn't change from up to down or down to up. So you have to have that change in concavity. Okay, there's two other things that you would encounter, like here you're concave up, and then you're changing to concave down here. And again, what happens is that is an inflection point because it changed from up to down. And what happens on this is this second derivative does not exist. Do you have any idea why? It has a vertical tangent line, exactly. Okay, so there's going to be times when the second derivative doesn't exist, just like the first derivative doesn't exist. And then notice on this one, this entire thing is concave down. Okay, both of those things are like kind of a frown or half of a frown. That is not an inflection point because the concavity didn't change. So an inflection point is just simply a point on the graph where the concavity changed from one to the other. Okay, that's all that is. Okay, right? What's that? Say again. Yes. Yeah, kind of like this one up here. If you made that concave down the whole way, then that second derivative would be 0 at that point right there, but it wouldn't be an inflection point because the concavity doesn't change. Okay, so that's the same thing. Okay, so here's the best way to remember this. is just these faces right here. So this is kind of what, to wrap up what we're doing, is this is how it goes, is like this. So if you can do this, you could do this on your next test, is if you want to remember how to tell something's concave up, you just make a smiley face, and then you put a second derivative tattoo on their cheek. And what that says is if the second derivative is positive, then you're concave up. That's how I remember that. Okay. Then if you got a sad face with negative eyes and put the tattoo on the dude's cheek, that's how you tell if something's concave down. Okay, so those two faces tell you how to analyze concavity. Okay, all right. So let's go to the next page. And before we take a break, I want to get through just an example to kind of start us off on this thing. Okay, so what we're going to do in this problem, now we've got a basic function that's easy to work with because you use power rule when you do the derivative. So actually, we're going to kind of put a lot of things together on this problem. We're going to analyze where it increases and decreases like we learned. We're going to look at where we have max and min like we learned. And then we're going to look at concavity now. Okay, so let's go ahead and just do the derivatives first of all. So the first derivative on this is 20x to the third minus 60x to the second. We're not going to do anything with that yet. We'll work with that in a minute. So what's the second derivative? 60x to the second minus 120x. Okay, so second derivative just means do a derivative again. Okay, and that second derivative, basically what happens is the first derivative is how we look at where the function increases and decreases, and the second derivative is looking at the concavity. Okay, so we're going to do actually a couple of sign charts on this problem and do that. Okay, so we're going to do critical numbers for each derivative. Okay, so we're going to go ahead and just write down your first derivative and set that equal to 0. And then we'll solve that to get a critical number. Okay, so how do you solve that equation? Factor out what? 20x squared. Okay, and what's left? X minus 3. There you go. Okay, so you got a factor. Okay, can you do that in your head as to what the two critical numbers are? 0 and 3, right? Okay, and I'm okay with you just, doing that in your head. You're going to get x equals 0, and then if you have x minus 3 equals 0, then you get x equals 3. So you do have two critical numbers on that. Okay, now what we're going to go ahead and do is, since we're going to also do concavity, now go ahead and take your second derivative and do exactly the same thing. Okay, just set that to 0. And these problems are generally easy to do if you can factor. Okay, so you can take a factor of 60x out of that, and that would leave x minus 2. So you would get 60x is 0, and then you would solve x minus 2 equals 0. So you end up getting x equals 0 and x equals 2. Okay, so once you get your derivatives, you always do your critical numbers. Okay, now what we're going to do is we're going to do sign charts, and we've learned how to do sign charts. So this kind of increase, decrease stuff is not new to you. So down in this step number 3, we're going to work with the first derivative. So the two critical values on this were 0 and 3. So you just want to do x equals 0. Then you want to do x equals 3, like that. Okay, now what do we do with this sign chart? What did we learn how to do? Plug test points into what? Into the first derivative. Okay, so what we're going to do is we're going to take, just pick some test points. Pick anything you want to less than 0, like -1, and then you can plug that into that first derivative, and you can plug it into the original or the factored form. It doesn't make any difference to me which way you do that, so I'm just going to plug it into that first derivative. And then again, something like that, if you want to do that on your calculator, you can. If you want to do it on scratch paper, that actually is just 20 times -1 minus 60 times 1. So that's -20 minus 60. So that's a negative. Okay, what does that tell you about the graph? Increase or decrease? Okay, good. That means that we decrease. Okay, so we just do that. Okay, now let's go with a test point between 0 and 3. Let's go ahead and use 1. So again, plug into the first derivative. So we'll do 20 times 1 to the third minus 60 times 1 to the second. Okay, that's negative. So what are we doing? We're still decreasing. Okay, so we know that. Okay, just plug your test points in. Okay, then finally we'll use a number that is bigger than 3, like say 4. You plug that into that first derivative, you'll work out 20 times 4 to the third minus 60 times 4 to the second. Go to your calculator if you need to. You'll get positive. So what does that tell you? That we're increasing. Okay, so that's nothing new. I'm just kind of reviewing what we did a couple of sections back, and then we can go ahead and answer all of these questions below. Okay, so increasing, what's the interval going to be for increasing? Okay, 3 to infinity, good. Okay, and how about decreasing? What's that going to be? Not quite. You have to do 2 intervals. There you go. You can't do one whole interval because when x is 0, the derivative is 0. It's not negative. X equals 0 is kind of neutral, so you have to write this as negative infinity to 0, union 0 to 3. So be careful about that. Okay, you can't just use one interval. That's technically not correct. Okay, now, again, what you're trying to do on here is you're trying to do all this without graphing. And if I look at this sign chart, this is what the sign chart's telling me. I'm decreasing, then the derivative becomes 0, so it levels off. Then what happens? It decreases more, then it levels off, then it starts increasing. So again, that sign chart tells you what the graph looks like. So is there a local minimum on that problem? Yeah, what's the x value of the local minimum? Right here, there's your minimum right there. That's at 3. Okay, remember what a local minimum is the graph changes from negative to positive. Derivative goes negative to positive, you decrease, then increase. Okay, do you have a max? No, what's a max? A local max means the sign chart has to go from plus to minus. You have to go from increase to decrease, so we've got nothing there. Okay, now what you can do on this now is if you want to find the y value of the minimum, you just need to plug the 3 into the function. So I'm just going to kind of do this at the side here. You can even do this on the calculator. So if you do f of 3, you would do 5 times 3 to the 4th minus 20 times 3 to the 3rd plus 10. And then you could use your calculator to kind of work that out. But you could also graph on your calculator and just trace that out. So I'll do 5 times 3 to the 4th. I know 3 to the 4th is 81. And then minus 20. And 3 to the 3rd is 27. And then plus 10. And then that will give the value of that minimum. So that's at negative 125 is where that occurs then. Okay, so we've got everything that we need about the first derivative answered the questions about increase, decrease, local min, and local max. Okay, now I think on your handout I gave you this graph. So one thing that you probably want to do on here is just label this point right here. That point is the point 3, negative 125. So that's where your local min is. Okay, that's what that graph is going to show you if you put that in your calculator. Okay, any questions so far? Okay, so if you're asked to look at increase, decrease, and that's all about the first derivative. Now we're going to do the new thing, which is the concavity. So down in this step 4, what we want to do is you want to draw a number line, and then this time, the second derivative was equal to 0 at 0 and 2. So this sign chart, you're going to work with x equals 0. That's where the second derivative was 0. And then you're going to work with x equals 2. And that, again, is where the second derivative is 0. Okay, so 0 and 2 could be inflection points. They could be. We're not going to know that until we finish up this sign chart. So now it's just kind of a matter of using test points. Okay, where do I plug the test point in on this thing? Second derivative. Okay, so plug that in to the second derivative. Okay, and I'm just going to kind of do this at the side. So if I do f prime of negative 1, I'm doing 60 times negative 1 to the second minus 120 times negative 1. That'll be 60 plus 120. That's positive, so that means you're smiling. That means the graph is concave up. Okay, all right, you are happy. The graph is happy because the second derivative is positive. Okay, so that's what that tells you. Okay, now let's take a test point between 0 and 2. Let's go with 1. Okay, now again, you're plugging these into the second derivative. So if we evaluate the second derivative at 1, we have 60 times 1 to the second minus 120 times 1. That is negative 60. So all that matters is the second derivative is negative. That means it's sad. Okay, think of that sad face I showed you. So that means you are concave down. Okay, that's what that's telling you. And then finally, we'll take a test point bigger than 2. Doesn't matter as long as it's bigger than 2. So we'll evaluate the second derivative at 3. Okay, so we'll do 60 times 3 to the second minus 120 times 3. That would be, doesn't matter. I think that's going to be positive. And again, if it's a little hard to do in your head, just use your calculator if you want to. So that would be 60, 3 to the second I know is 9, and then minus 120 times 3 is 360. Okay, so you should get a positive on that again. Okay, so then we have that goes back to positive. That means we're concave up. Okay, so it's the same thing. You're going to be doing sign charts, but the second derivative analyzes concavity for you then. Okay, so where am I concave up? What is the interval? Negative infinity to 0. What else? 2 to infinity. There you go. Okay, concave down, where is that? 0 to 2. Okay, do you have inflection points? Did the concavity change? It changed 2 times, didn't it? So you have 2 different inflection points. You have 0 comma something, and you have 2 comma something. So again, that changed. So what you have to do now is you have to just plug those things in, okay? And what I'm going to do now, you can save yourself a lot of time if you just kind of, as you're doing the sign chart and test points and stuff like that, you can just kind of look at the graph. So I'm going to go ahead and just put the original function in, which is 5x to the 4th. And let's see, minus 20x to the 3rd. And what else? Plus 10. Okay, so I'm just going to do kind of a standard graph. I'm going to go ahead and graph that. For a window, well, let's see, the critical numbers were 0 and 3 and 2. So maybe if we just go like negative 5 to 5, like that. And let's see, we did end up getting, the local minimum was negative 125. So I'm going to do like maybe negative 150 for the minimum y, and then maybe 150 for the y, and then maybe scale that by 50. Okay, so you got to kind of play with the window a little bit. Then if you graph that, then we can get those inflection points and change it and kind of check at the same time. So what we figured out, our sign chart said that at x equals 0, that's a point of inflection. So if I trace at 0, that'll give me the point 0, 10. Okay, does it look like my graph is changing from concave up to concave down? Yeah, okay, this part right here is concave up. This part here is concave down. Okay, so it is changing. Now trace at 2. So if I trace at 2, we'll have the other inflection point, which happens at 2, negative 70. So it's real easy to get the y value of your inflection points just by graphing anyway. Okay, so what's really happening on this, what you want to put on this graph I gave you, I would just label that point as 0, 10, and label this point right here as 2, -70. And then you want to kind of maybe make a note to yourself how the concavity changes. You're concave up in these two locations that I highlighted in yellow, then you're concave down in that little location right there. The inflection points is telling you where the concavity changed, okay? Now, I want to stand up and kind of show you something on this because on my calculator here, because it's kind of hard to show this without kind of pointing something out on the graph. But see, you're concave up from 2 to infinity. Now, here's what you want to understand is this tangent line. This is representing the slope of my tangent line. Right now, isn't that tangent line negative? Right now it's 0, so it's getting bigger, isn't it? Right now it's positive. So this thing is going from a negative value to 0 to positive values. So the slope of the tangent line is getting bigger. That's what concave up really means. The other place you're concave up is from negative infinity to 0. Okay, right now you have a negative sloping tangent line. And it's going to continue to be negative, but eventually it's going to be 0. So it's getting bigger. Okay, right now, I don't know what that tangent line slope is. Maybe it's -100. But it's getting bigger because the slope is becoming a smaller negative number. That's how that goes. And then if you're concave down, which is this piece right here, look at what happens to this tangent line. Right now it's 0, then it becomes more negative. So that's really what concavity is it's a measurement of how the tangent line is changing. Does that make any sense? Okay, it's a little harder to see the negative. This part right here is pretty easy to see. That tangent line gets bigger and bigger and bigger. That's what concave up is. Okay, and the other thing I wanted to point out is when you're doing a graph, when you have a point of inflection, anytime you have an inflection point, see how that tangent line slices through the graph. Part of it's above the graph, part of it's below. That's what it looks like. Same thing happens at this point right here. That's an inflection point. The tangent line would go like that. Part of it's below, part is above. So it slices through the graph so that part's above and part's below. That's what a inflection point's tangent line looks when that happens. Okay, all right, any questions?